right?
Yeah.
That's two separate tires?
Two separate tires. I think. He texted me and said, you're never going to believe this. I know flat.
I know. He sent.
I
know. He sent me an email and he's like, "You're not gonna believe this." He's like, "But I hit another." He's like, "I got another flat." I was just flabbergasted. I was like, "I cannot believe." Is it just like the tires that he messed up?
I don't really know. You just sent me like, "You're never gonna believe this."
Yeah. Well, hopefully it's just the tires, because when I got my flat earlier this semester, it's like the rim got all messed up. I had to take it to a place because when I went to the Kia dealer, they quoted me like $1,000 just for the rim and tire. And I was like, I'm not paying that, no. All right. So just before we get into our next discussion, just a reminder, your exam 2 is coming up in 2 weeks. It is on the 15th. Everyone can create their formula sheets. Granted, I want everyone to kind of work together on making the formula sheet, so you guys have freedom to put whatever you want on there as long as there's no example problems. But everyone has to use the same formula sheet at the end of the day. So I highly encourage all of you to kind of coordinate with one another to figure out what equations to put on the formula sheet. And then obviously if you want, you can send it to me for review and I'll tell you if it's good or not. All right? So yes, just make sure you all are going to be sending me that formula sheet before the exam, and I will provide a copy of it during exam day, so you guys won't have to print it out. All right? So, today's discussion, we will be talking about shearing stresses in beams and thin-walled members. So, as you guys remember from last lecture, or the last few lectures, I will say, chapter 4, we talked about bending stresses in beams and how bending moments contribute to axial forces within the actual member. However, in chapter 5, we learned that beams aren't just explicitly subject to bending moments, but also shear forces within the beams themselves. Now, we didn't discuss how the design of these shear forces go, which is what today's lecture is going to be talking about, is how to design beams for both shear on top of contributions to flexure. So, just to start off, again, just as a little recap, if we were to draw the shear force and bending moment diagrams for this, if this wants to work, it's like telling me not. Actually, just X out of that, just draw the shapes really nicely. It's telling me I can't save a copy. Interesting. There we go. That should work now. Yes. All right. If you guys recall, for the shear force and bending moment diagrams, wow, I'm really going to hate this. I got to discard. I'm actually just going to work using the ruler here, so I'm not going to present. So if you guys recall, we learned last class and the last few classes how to draw the shear force and bending moment diagrams. From this loading shown here explicitly, the load is directly at the center. So what we should end up with is basically a shear force diagram that looks exactly like this. The shear force is going to be equal to F divided by 2, and then negative F divided by 2. And then from there, we learned that you can actually draw the bending moment diagrams using the geometry of the shear force diagram, and that bending moment diagram is just going to equal FL divided by 4. All right, you can do all of the cutting sections to derive the equations for each of the curves, but once you start getting so familiar with a lot of these diagrams and the standard conditions, you actually just start memorizing a lot of the equations. So I memorized this one and probably like 50 other ones. You just get very comfortable with it. All right, so we learned that from the bending moment diagrams, we would just use the my over I equation or the m over s equation to analyze the beam in bending. But for shear, we still don't know how to exactly design this beam, all right? We know from from like the very beginning of the semester, we have our average shear stress equation, which is V over A, right? So we could potentially use V over A, but the shear stresses are actually going to be a little bit more complicated than this, especially in flexural members, which is what we'll get into. All right, so for transversely loaded beams, what we have, here, let me see if I can zoom in. What we have are shear force and bending moment diagrams, and if we analyze a small little cube up towards any particular extreme location, right, what we end up with is actually that stress block, which hopefully you guys realize is something related to the Mohr circle. So we could actually draw Mohr circles for beams that are subjected to shear and bending. So in this case, what we actually have is basically, in some instances, towards like the extreme top fibers, this is kind of like messed up a little bit, is actually towards the top and bottoms of the beams, the maximum location of which bending stresses occur. You'll actually find that the shearing stresses on those edges is actually 0. We'll get into a little bit about why it's 0 and the mathematics behind it. But ultimately, we can basically determine that under pure bending, the shear force is basically 0, because when a member is subjected to pure bending, then the bending moment diagram you would see, it would actually be a constant value. So a good example of this would be if we have a beam here with a cantilever support, and then just a direct moment is applied. In this case, you would actually find that your reaction force is 0, and hence you would just have a negative moment directly here. Now in this case, if you were to draw the shear diagrams, you would find the shear force diagram is just 0. There's no vertical forces contributing to shear, but our bending moment diagram would just be a constant block like that. We called this pure bending, which is what we discussed in chapter 4. You just never really saw it from a chapter 5 perspective. All right? So that's why we have basically no shear force whenever we're subjecting a beam to pure bending, because there's no shear forces to contribute to shear stress. All right? So we basically move on a little bit, and ultimately what we would find by analyzing like the equilibrium of these little nodes here, you would find that from some of the forces in the x direction, we know that that has to equal 0 for equilibrium. You would just find that the integral of tau xz, that's this shear force that's located right here, so it's coming out of the plane, times dA, that has to equal 0. But if we do some of the forces in the y direction, however, oh wait, no, that's some of the forces in z. Yeah, because technically some of the forces in x would give you the normal stress. My bad. So from some of the forces in the y direction, though, you take an integral of tau xy dA, and that integral should technically equal negative v. So the shear force is just, or plus v. So the shear force is just equal to the negative integral of tau xy dA from over the area. Does that make sense so far? If you think about it, the cross-sectional shear force is just going to be acting downwards, v. The shear stress that's located here is tau xy dA. So when you do some of the forces in y, you get that the shear force should just equal the integration of the shear stresses within the cross-section. All right. Now, we learned previously how some beams may ultimately fail in bending One of my favorite examples that I like to personally sketch out is generally with concrete beams, right? So let's say we had kind of a concrete beam just right here. In many cases, if you were subjecting a load directly downwards, you would actually find that the cracking is heavily dependent on the type of failure. So for example, bending cracks, where do you think bending cracks might most likely occur? At the bottom, where along the bottom?
The midsection.
Exactly, because that's where the maximum bending stresses are going to occur, which is going to result in the maximum tension within that concrete beam. So you would actually see cracks start to develop. Now, when it comes to shear forces, however, concrete's a little unique, so the shear plane is going to be a little bit weird looking, but for steel and other metallic structures that behave more linear elastically, the shear planes would actually just be just cracks that are propagating like that. For concrete, it tends to move on a 45-degree angle, but for shear cracks, you would actually see that the cracking is occurring more towards the end sections more than anything else. Does that make sense? All right. So now just going into a little bit of the math, shear on a horizontal face of a beam element. This is basically just looking at the shear forces that are directly vertical on that face, which is going to be the YZ face. This is assuming the X is along the length of the beam. We consider it as a prismatic beam. So you consider AB as a prismatic beam, which means it's just a relatively simple shape and it's uniform in terms of the material properties. When you analyze the internal forces at a particular point, in this case, that point is going to be defined by our little stress block, more circle again, C, D, C prime, and D prime. You determine that you have both normal stresses, which are the sigma C and sigma D times dA due to the bending stresses, along with shear forces that are ultimately going to be present along the sides of that block. So when we do sum of the forces in the x direction equals 0, that delta H is going to be a term which we call shear flow later on. Basically, that delta H term is then added to the area underneath that axial stresses, which that total force is going to equal the integral of the sigma C minus sigma D times dA. So that's the summation of the two stresses times their associated areas, which the areas should match. Which then, when you break this down, you would find that that delta H term just equals the bending moment at point D minus the bending moment at point C divided by I times the integral of y dA, my over I. Now, hopefully you guys know this by now, but if you notice, the integral of that y dA is equal to the first moment area of inertia. We use Q to generally define this. So this is the first moment area of inertia. Hence, we can kind of elaborate these expressions to then be the difference in the bending moment is equal to dm over dx times delta x, which in turn equals the shear force multiplied by our width delta x, where delta x is just the width of our little rectangular block. let me just paste this and erase all of this now. All right. And so performing that substitution with knowing this term here into that delta H equation back up here, we would actually find that delta H is just equal to VQ over I times delta X, which is the horizontal shear force that's felt by the beam. This is ultimately how the shear forces get transferred directly to the reactions. They have to be carried some way into the beam. So that's why when you draw out a lot of these diagrams, you kind of have positive and negative. It just indicates that the directions in which the shear is being carried is going different directions, if that makes sense. All right. Now from here, we can actually break it down on a per unit length term. So what we end up with is this new term we call Q, which is just equal to delta H over delta X, which simply breaks down back to VQ over I. And this we call shear flow, which is just the force per unit length. Any questions about this so far? All right. So with our shear flow ultimately determined, shear flow, which is equal to Q equals VQ over I. You need to note that Q is just equal to the integral of Y dA. Recall that the second moment area of inertia is equal to the integral of y squared dA. This is your statics. And ultimately what you would find is even if we analyzed the forces all along the bottom, the equation will still hold true. So even if you considered C prime, D prime, C double prime, D double prime, you would still get that basically just Q is just equal to negative Q prime. So the shear flow would just be equal but opposite in sign. And then delta H is just equal to negative delta H prime, which those are just the shear flows that are basic, or the shear forces basically felt by the bottom part. So they have to be equal and opposite to each other. All right, now you might be wondering, in what way does shear flow ultimately come into play? We're designing for a shear force that's acting horizontally, but we still need to analyze the shear forces acting in a vertical cross-section. One such example that you would typically see shear flow is if you had built up members that had some type of nailing directly into the floor, into like a vertical element. So a good example would be like wood beams. Maybe you have like a floor deck that you're basically nailing directly into a beam, and you need to design for the shear forces within the nails transferring. Another good example might be if you guys ever see like those composite concrete and steel decks. A lot of times those steel decks actually have welded studs on top in order to provide bonding to the concrete. And so there's shear flow that's actually within those studs that ultimately need to be designed for. So analyzing this, we could determine what the shear force within each of the nails are using our principles of shear flow. So hopefully you guys should just be able to notice that this is a directly symmetric cross-section. So our Y bar is just basically going to equal 70 millimeters. 100 plus 20 plus 20 divided by 2 is 70, right? Now, we also need a few other terms. We need to recall that Q is equal to VQ over I. I is the second moment area of inertia of the entire cross section. So what we need to do is compute I for the cross section. This I, if you were to develop the tables, we could actually just do that. So component A dy, A dy squared, and then Ix. We could have the top flange, the web, and then the bottom flange. The area of the top flange is going to be 200 millimeters squared. Same with the web, and same with the bottom flange. The location of the neutral axis of the top flange is going to be 50 plus 20 divided by 2, so that's 60. Web is at the neutral axis directly, and then bottom flange is just negative 60. Let me get a calculator real quick because I can't do basic math in my head. 200 times 60 squared gives you a really big number, 720,000 and 0. And then for Ix, because this is all rectangular, use BH cubed over 12, where the base would be 100, height is 20, cubed divided by 12, which gives you for this 66,667. And then for the web would be 20 times 100 cubed divided by 12, which is 1,666,667. And so when you sum all of these together, you should ultimately get that Ix total is roughly 1.62 times 10 to the negative 5 meters to the fourth. I'm just doing a conversion. I'm too lazy to do the actual conversion myself. Are there any questions so far about this? All right. Now that kind of begs the question is, what is Q? Q is actually heavily dependent on the position in which our shear flow is ultimately occurring. In this case, the shear flow is actually occurring right at the interface of the top web, or the top flange, and the web. So our shear flow is occurring right here and right here. Fortunately, because it's symmetric, we only need to calculate the shear flow for one section. All right? The way that we do that is we ultimately just take the area above the region that we're interested in. All right? And so, that Q term, I generally like to define this as A tilde times Y tilde, where A tilde is basically the area above our point of interest. That's going to be that grayish shaded region here. And then Y tilde is basically the center of that block from the neutral axis. So A tilde just equals the 100 millimeters times 20, 2,000, which is the equivalent of about 2,000 millimeters squared, so 0.1, hold on, times 20 divided by 1,000. So 2 times 10 to the negative 3 meters squared. And then that Y tilde is just equal to 0.060 meters. Again, that's the 70 meters, and then you have to subtract halfway of the flange to give you 10. All right, doing this, you should get that your first moment area of inertia at that region is 1.2 times 10 to the negative 4 meters cubed. With that in mind, we can now actually calculate what the shear flow ultimately is. So, not V. Lowercase q, shear flow, is equal to the shear force, which this problem tells us is 500 newtons. Q is 1.2 times 10 to the negative 4 meters cubed. And then I is the entire cross-section, so 1.62 times 10 to the negative 5 meters to the fourth. And what we end up with is a shear flow of 3,704 newtons per meter. Now, what does that shear flow ultimately look like? It's basically just think of it like an axially loaded distributed load. So that shear flow is basically a magnitude of 3,704 newtons per meter. All right? And that's basically felt at every single point along the interface of our two sections. Now, our nails need to be able to carry each of that, which means that they're going to have each some tributary width, we call it, which is basically some area of influence in which the load goes directly to the nails. What we do is basically for each nail, we know that for one nail, the shear force that's felt by it is just equal to the shear flow, and then that delta x would technically be our quote-unquote tributary width, which, not delta h, which that tributary width, conveniently, is that 0.025 meters. So the shear force felt by one nail is just going to equal the 3,704 newtons per meter multiplied by 0.025 meters. You can write meters per nail if you want to. That should help with clarifying things. So 3,704 times 0.025 gives us a shear force of 92.6 newtons per nail. And that's ultimately the design force for every single nail that you would basically design for. This still doesn't tell us the shear force for the entire cross-section, but it does help with analyzing connecting members within a particular cross-section. Make sense? All right. I have another example here. This time we actually have two nails, and it's a built-up box section with some shear force V. So in this case, I'm just going to give you guys the I and the Q for this. So the I for this built-up cross-section would just equal 2 times 1 over 12 times the thickness of each member times the height cubed. That is ultimately going to be the term used for these values here, plus 2 times 1 over 12 WT cubed plus WT times 1 over 2H plus 1 over 2T squared. And that is for these regions, the top and bottom flanges there. So that's blue, and this is red. Now, if we wanted to analyze the shear force per nail, there's a few ways that we can ultimately do this. the first method is by just taking the block at the interface above it and just taking the areas with respect to that region. So by doing this, we would ultimately get that the shear force is equal to Q times, in this case, the delta X term is being set equal to a nail spacing of D. So Q times D, which then just gets simplified to VQD over I. Now we need to keep in mind that in this case, there's actually two nails within the cross section. So each nail is going to carry some shared portion of that load. So the force that's actually per nail is just going to equal delta H over 2. Two nails at interface. Which means that our ultimate design force would be VQ D over 2I. Does that make sense? Why we're dividing it by 2? If you had 3 nails within the interface, then you would just divide it by 3 and so on and so forth. Now, what about in the event that we take Q equal to this? How would we rationalize this? What do you guys think? What would Q be? Like, what would the shear flow be in this case? Let me ask this first. What would our first moment area of inertia be for this section? I'll give you guys a hint. What's that y tilde term, which is the distance from the neutral axis, or the center of this shape from the neutral axis? 0. So what would Q have to be?
0.
Exactly. So the first moment area of inertia of that section there would actually be 0. What does this mean about our shear flow and the shear force per nail? Remember our equation, Q equals VQ over IB. What does this tell us about the shear flow? Exactly. So Q equals 0, lowercase q equals 0. I'll tell you why that is. That's because when we analyze the neutral axis, all right, and we draw the forces above and below the neutral axes, the net areas, the forces are going equal and opposite to each other. So the net shear flow that's felt within that shape, both top and bottom, is going to sum to 0. Whereas previously, we actually had this top section here, which means our entire shear flow was all just acting in one direction. Because the shear flow then was, let's say, positive up here and then negative down here. But we're not analyzing it on a symmetric level, if that makes sense. Instead, you're just analyzing it per unit area. Does that make sense? There's no area to take underneath the neutral axis because the area is limited to that top flange. So that's a good note to add. It's because the result is the net total shear per unit length on the selected interface. And then basically the shear top is equal and opposite to the shear on the bottom. Now, another interesting thing, it's actually not even really on the notes, but if for this equation here, the same area, if we wanted to, another way that we could analyze the shear flow along this plane, basically up here, would be if we took this total area here. Because then the plane of interest, as long as we're not adding the top blue and the red, we should get exactly the same value. So really, that summation, the only reason why it cancels is because our point of interest is technically being taken at zero, at the neutral axis. So you always want to make sure that you're only selecting one side of the region. Any questions about anything that I've discussed so far? I know it can be a little bewildering. Don't worry, it gets worse. All right, so that's basically how shear flow ultimately works. It's just the force gets carried horizontally along the length of the beam, and from there you can design like welded stud anchors. You could design like I don't know, the nails in like a floorboard system, so on and so forth. Let me just check to make sure that I'm not like rushing through this, because if not, then I'll continue. Okay, so we could do 6.2 up to 6.2 then. Awesome. That is what it's just said, right? Up to 6.2. Yes. All right. Next section now is just talking about shear stress in a transversely loaded beam. So this is technically the shear stress in the actual cross section felt by the actual beam, not the shear flow, but the actual shear stress. So we analyze the cross section, we look at the internal forces, and we ultimately cut a section. If you guys recall, that delta H term, which is the shear force, we set that equal to VQ over I times delta X, where delta X is, again, the width of the region that we're interested in, our tributary width for like a nail or a bolt or whatever. All right? So from here, we compute the average shear stress on a horizontal cut face. We set this equal to the shear force, and then, of course, we divide it by its associated area, where delta A is just this small region here. Everyone should hopefully recall shear force is equal to force divided by area, but we're doing it on such a small infinitesimal region that everything's just going to approximate out to something more exact. So we expand upon this. Delta H prime was VQ over I times delta X. So VQ over I times delta X divided by delta A. Expand this further. We know that delta A is just equal to basically delta X times the thickness there. If you got, I know it's kind of hard to see, but that dimension is generally going to be fixed in a cross section. So it's whatever the width of your cross section is at the point of interest. So that's always going to kind of be a known quantity or something that you can solve for. All right? The delta x's cancel out, which in turn results in our general shear stress equation, VQ over IT. Some textbooks refer to T as being B, but the general idea is that it's just the width at the point of interest you're interested in. All right. So if we take a cut along the upper or lower surfaces, what we would actually find is that the first moment area of inertia would ultimately be 0. That's at the upper and lower surfaces, so the max points. The area is technically 0, which is why the shear stress at the top and the bottom is equal to 0. Does that make sense? Because if you look at a cross section and you're taking your Q term all the way up at the top, you'll find that your A tilde term, there's nothing to take. So let's take a rectangle and you want to analyze the shear stress directly at that point, right? Let's say that this is our neutral axis and we want to observe what the shear stress is. You need the area of that. And then your neutral axis, Y tilde, would be this. But what's A tilde? There's no area, right? It's just 0 because it's just, there's nothing for the shear force to carry. It's just, yeah. So because of that, what we end up with, Q is equal to 0, which in turn is the reason why the average, that shear stress at the top and bottom of the beams is almost always going to be 0. All right, so while the shear stress might not be constant along the z direction, again, if we analyze those stresses, it doesn't necessarily mean that it's 0. It is a reasonable approximation if the width of the beam is small enough compared to the height to assume that. So for a rectangular beam, the maximum shear stress is less than about 0.8% greater than the average. So because of that, you can generally make very good approximations with everything, not to mention the horizontal shear stresses also just aren't a concern in general. So those are the shear stresses felt in the z direction. Does that make sense? Yeah. So I've got some examples here of basically how the shear stresses look like, and I even actually one of the things that I created is an Excel spreadsheet to help you guys analyze, to visualize the shear stresses along a cross-sectional axis of the beams. So I'll probably provide you guys with some of those probably after class today. Otherwise, feel free to make some of your own if you want to. I think it's fun to do that. But basically, shear stress in an narrow rectangular beam. This is just one example of how to calculate the general shear stress, and what we're going to see is a comparison between what the general shear stress equation provides, the VQ over IT equation, versus the average shear stress equation, which is just a simple V over A. You guys will actually see how much of a big difference it is. So hopefully we should recall that so let's say to calculate the maximum shear stress, the maximum shear stress is always going to occur at the neutral axis. That's because this area is ultimately maximized. All right, so tau max is at the neutral axis. So our Q term, which equals A tilde times Y tilde, this A tilde term, which is the shaded red, is just going to equal B times 1 over 2 H. So it's equal to BH over 2. Let me actually shift all of this down just because that's not technically Q. It's not moving. So A tilde was equal to BH over 2. And then Y tilde is just equal to H over 4, because that Y tilde would be located directly here, which is just going to be H over 2 divided by 2, which is just H over 4. All right, so we plug all of this in, and what we end up with is BH squared divided by 8. All right, from here, we know that the second moment area of inertia is equal to BH cubed divided by 12. And so when we compute the tau max term is equal to V times BH squared divided by 8 divided by BH cubed divided by 12. And that's multiplied by the width at the point of interest, which, because the beam is uniformly the same width B, our point of interest is always going to be that width B. From here, we could do some simplifications, but what we should ultimately find is, hold on, did I do this right? I just want to make sure A tilde would be H over 2 times B. Yeah, and then Y tilde is just H over 4. I think that's where I'm going. No, I'm right. Let me just double check something, just because I feel like this isn't working out for some reason. Oh no, it's right. All right, so basically all of this is just going to end up simplifying to 3 over 2 times V over B times H. All right, you can do the math to double check. I just had to check to confirm by myself. But if you guys notice, this is just equal to 3 over 2 times the average shear stress. So what you guys observe is that the maximum shear stress is actually 50% higher than the average shear stress that we were initially considering. For prismatic beams like this that are relatively simple shapes, this is a very significant concern, which is why you generally want to consider the maximum shear stress over just the average shear stress. Because if your shear force is very high and you're in an element that's very critical, the last thing you want is that thing failing due to the fact that you undersized it by about 50%. All right? So we can actually plot the curve, and when we generalize this equation, like I just did it just for the maximum shear stress case, but what you would ultimately find is if you analyzed it on a per location basis, the derivation is actually in the notes, but I'll just write it here. 3V over 2A. Actually, I'll just write it differently. 3 over 2 times tau average times 1 minus y squared divided by c squared, which would be if instead of just analyzing it at a particular point, you were analyzing it at a variety of points, and then you maybe wanted to plot it in Excel to analyze how those shear stresses really vary. What we would ultimately see is this quadratic distribution, which obviously makes sense because our entire plot is heavily dependent on that y value. So the shear stress is ultimately dependent on the horizontal coordinate from the neutral axis. All right. Now, using my spreadsheet that I actually made, we can actually see numerical values for what this would be approximated to. So if we assumed that the width of that beam was 8 inches, the height of the beam was around 12 inches, and we had a shear force of 7,000 pounds, the maximum shear stress that was computed was around 109.375 psi, whereas the average shear stress was 72.917 psi. So it becomes a very significant difference, which is why always just account for the maximum shear stress. Now, there are some exceptions, like in the case of wide flange beams. There's actually a reason why we use wide flange beams, and that's because their shape ultimately allows for actually a simplification of some design aspects. Not to mention the web itself doesn't really need to carry normal stresses. If you guys remember, the maximum normal stresses are always at the flanges, but obviously the web forces are going to be small for normal stresses. Now, knowing what we know, we know that the normal stresses within the flanges might be great, but the shear stresses are actually going to be really small. This is because when we have our equation for tau is equal to VQ over IT, you'll notice that for the tau and the flange, the T is actually much larger. So the tau and the flange is actually much smaller than tau for the web. And that's because that value of T is the difference between something like 10 inches to like half an inch, for example. I just spit out some numbers, but you guys can see how that significant difference can really impact the magnitude of the shear stresses. That's why we ultimately have this giant jump here. Do you guys see that? Because then your unit width isn't necessarily just one unit width, it's the width at the point of interest. So if you're in the flange, the width would be that giant value of T, which is the flange width. But if you were in the web, it's just whatever the thickness of the web is. So that's why we have that immediate jump that occurs right there. And what we'll actually find, interestingly enough, is in practice, especially, so for those of you who are planning on going into structural engineering for like building systems and will commonly be using this methodology, you'll actually find that tau max is actually approximately the shear force divided by just the web area. All right, now you might be wondering, how do we know that? Easy. I made an Excel plot. All right, so I threw in some arbitrary geometry in order to create a general flange section. In this case, the flange width was around 10 inches. The flange depth was around 10 inches. So the web height was around 8 inches. Let me see if I can't like sketch this out. So this was, oops, it's off. So this was like 10 by 1. Then this shape here was around 2 by 8. And then this shape here was also 10 by 1. All right. Now, when you use VQ over IB, you can actually calculate, I do it on an iterative basis, so I just calculated it on the shear stress per point. And what you ultimately find from using VQ over IT is that the maximum shear stress is around 433 pounds per square inch. But if you just took the area of the web, which is just going to be the 2 times the 8 inches, you actually get an average shear stress around 437 psi. So it's a very small difference, which is why when you're generally dealing with W shapes, just take the area of the web, take the shear force divided by area of the web, done with the problem, nice and easy. Make sense about that? Awesome. Now, time for some practical examples, all right? We've got a beam here that supports a load shown. We want to apply a factor of safety of 2, given that the allowable stress is 10 megapascals. and that the allowable shear stress is around 500 kilopascals. All right, so we ultimately want to conduct a full beam design, basically. We're given that the width of the beam has to be 5 centimeters, so just what's the height, all right? So what we should ultimately be able to do by now is draw out the shear force and moment diagrams. So let's do that really quickly. We know that because of the symmetric loading, that each reaction force is going to be 1,000 newtons, right? So we could follow our tip to tail method. 1,000 newtons closes out, negative 1,000 closes out. Positive, negative, and each is 1,000 newtons. I wrote 100 newtons on accident. That's our shear force diagram. Now for our bending moment diagram, we can take the area underneath each part of the shear force curve and draw out the bending moments. So we can calculate the bending moment of, let's say, 0.1, 2, and 3. So M1 would just be equal to the 1,000 newtons multiplied by 1 meter, which gives you 1,000 Newton meters. Because it's a rectangular shear force plot, it's going to be a linear bending moment plot. M2 is just going to technically equal M1 because there's no shear force to add. And then for M3, it's just going to equal M2 plus the negative 1,000 newtons times the 1 meter, which closes it out to 0. So our bending moment is 1,000 Newton meters. If you guys notice, that center region between the load is an area of pure bending because there's no shear force located there, and the bending moment is constant. So for our design forces, we're going to have sigma max is, or not sigma max, let's say M max is equal to 1,000 Newton meters, not shear tau max, V max is equal to 1,000 newtons. Any questions so far about how the diagrams were ultimately obtained? Hopefully everyone should be able to do that by now. Your homeworks are probably going to be a little bit challenging because I gave you guys some interesting problems, but hopefully everybody should get the gist behind how to draw these diagrams by now. All right, so with that in mind, we can calculate now what the required height of the beam is. Let's check bending first. So bending, which is from chapter 4, sigma allow is equal to my over I. Now we want to use an allowable, we want to apply a factor of safety as the problem said. So if we go back to our problem, our design forces are just going to be whatever forces are shown multiplied by the factor of safety. So in this case, factor of safety of 2,000 Newton meters, and then 2,000 newtons. Go back over to here now. We can rewrite this expression to then say that the required y, actually, we know that the second moment area of inertia is going to equal 5 centimeters times I. I want to just use basic units. So 5 centimeters divided by 100. It's 0.05 meters. My pen's turned off again. 5 meters times d cubed divided by 12. And then where is the maximum normal stress going to occur with respect to the neutral axis? Remember where the maximum normal stress occurs, not shear stress, normal stress. At the top, right, which because this is a rectangular cross-section, it's top and bottom, it's symmetric. So y in this case is just equal to d divided by 2. Throw all of this into our equation. We have 10 megapascals is going to be newtons per, meganewtons. Do I want to use meganewtons? I don't even know. No, let's just use very basic units. 10 times 10 to the 6 newtons per meter squared is equal to a bending moment, 1,000 newton meters, times d over 2, divided by whatever this is, 0.05 divided by 12. D cubed over 240. Solving for D, I am just gonna throw it all into a calculator real quick. Put x over 10, x to the power 3, divided by 240. Whoops. I'm going too fast. I get that the required depth of the beam when dealing with bending is still taking a little bit of time to load, but it should end up being, that's not right, is it? Oh, that's why. Yes, good point. Yes, thank you. First mistake of the semester. Now this calculator. 1,000 times 1 divided by 1. This should roughly be equal to 15.5 centimeters. Technically, if you use the official calculator, it would be 0.155 meters, which gives you the 15.5 centimeters. That's what I got on my calculator right here. Now, is that the end all be all? No, we still got to check shear. All right. So now we check shear, which is part of this chapter. And we know that if we just used V over A, we would likely be under designing it, right? So we use tau is equal to VQ over IB. And just for the sake of it, let's do a secondary check for what tau is equal to V over A would look like. All right. So for tau is equal to VQ over IB, we need to first know where the maximum shear stress is going to occur. Where does the maximum shear stress occur? I said it, I think, once. Where? Always at the neutral axis. So Q is going to equal A tilde times Y tilde, which if we zoom into this cross section here, our neutral axis is going to be D over 2 from the bottom, which means that our A tilde is equal to 5 centimeters times D over 2. And then our Y tilde is equal to D over 4, right? So what we end up with is 5 centimeters times d squared over 8, which, let's simplify this down to meters, so 0.05 meters times d squared over 8. So it's equal to d squared over 160. Our I is again just equal to d cubed over 240. We computed that for the normal stress. And then lastly, our width at the point of interest, which is going to be the point of the neutral axis, because it's a uniform width, just assume it's 5 centimeters. So 0.05 meters. So tau is equal to the shear force, which was 2,000 newtons for design, times d squared over 160 divided by d cubed over 240 times 0.05. And this all has to equal 500 times 10 to the 3 newtons per meter squared, because 500 kilopascals was the shear strength that was allowed. Throw all this into a calculator. 2,000 times x squared over 160 divided by x cubed over 240 over 5. And then your value of d, you should get equaling 0.12 meters, which is equal to 12 centimeters, which is the required depth. So which depth would we use? $15.5 or 12? Exactly. Go with the larger shape. Now, just for the sake of it, let's check V over A. All right. So this would just be the 500 times 10 to the 3 newtons per meter squared is equal to the shear force of 2,000 newtons divided by 0.05 times D. And what we should get using this approach is, let's see, 2,000 divided by 500 times 10 to the 3 times 0.05, 0.08 meters. So if shear governed the design, fortunately in this case it doesn't, but if shear did govern the design and you decided to just go with V over A, you would have significantly designed by about, what is it, 50%, I want to say? 33? No, it's 2/3. You would have designed it by 66.66667% of the required dimension. All right. Are there any questions about anything that we discussed at all? No? All right. I think ultimately we kind of got through basically everything today. Because next class is going to be 6.3 and 6.4. So I guess we can kind of end it a little bit early. But yeah, hopefully you guys understand the premise that the shear force is just going to be dependent on the location at which you're analyzing it. For uniform cross sections, you can see that the maximum shear stress is heavily dependent on the geometry and will in most cases be higher than the average shear stress. And then obviously shear flow is something similar, but obviously for horizontal shear that runs along the length of the beam, which you would use to design generally for like nails, studs, or other connecting elements if you were using a built-up section. All right, that's going to be it today. If you guys have questions, feel free to let me know or send me an email, or I'm having office hours right now if you guys have additional questions about the homework or whatever, or the project.